How's it going, Chem Stars? It's Mr. Zed and Z-Dog here, back at you again with some chemistry.
Live from Z Squared Studios.
As you can see, my COVID-19 hair is getting worse, and yes, I can now stick things in my hair.
Woo!
Look at this, everything goes in there.
Where is it?
It's gone, that's right.
Disappears.
All right, so today we are going to be talking about hydrochloric acid mixing with magnesium in a gas stoichiometry lab. Now, things are going to run a little bit differently. We have a whole bunch of stuff that we're not going to tell you about, the math and the reaction. This is the reaction. It's hydrochloric acid mixing with magnesium. It's not balanced because at the very end of this lab, you're going to put all of the pieces together to solve the volume of hydrogen gas that is produced from this lab. Okay? So what are we doing in this lab? Just a quick recap. We're mixing excess hydrochloric acid with a known amount of magnesium. And that's going to produce a product and hydrogen gas.
So today we're using an excess of hydrochloric acid. This is 6 mole per liter hydrochloric acid, so it's going to be extremely corrosive. So hence we're wearing the nitrile gloves.
Safety first.
Safety first. We're going to transfer 15 milliliters of concentrated hydrochloric acid.
You want a funnel there, Z-Dog?
To the discharge tube. We can use a funnel for extra care. I'm pretty steady.
I know, Z-Dog's, he moonlights in the summer as a bartender, so he's got good mixology skills.
Steady Eddie, they call me. When I pour, I rain. So
Why are we putting in the acid first? Like, what's the reasoning behind that?
well, the acid is more dense. It's going to settle to the bottom of the discharge tube. It's also going to allow us a little bit of a margin of safety in terms of mixing the reagents and not having our magnesium react too quickly. It will take a little bit of time for the hydrochloric acid to flow from the bottom of the tube down to the top when it's inverted to react with the magnesium arc.
So it's almost like a fuse.
Almost like a timing fuse, exactly. Give us a little bit of time to ensure safety. Slowly pouring distilled water into the gas discharge tube.
You gotta fill that bad boy all the way up, okay?
Fill it all the way up to overflowing. And the reaction is going to generate hydrogen gas, which is going to be under pressure. It's flammable, so we've got to take care with this. And that's going to displace some water in this tall bucket here to the right. Finally got the tube filled. We're going to combine this, react it with 0.06 grams of magnesium. We're able to use a centigram balance here, which is critical when measuring such tiny masses.
Recap the mass at the end of the experiment. But that's 0.06 grams.
So pretty critical to use precise tools in an experiment like this. Always something to add to the error discussion. What we've got next is a rubber stopper with a copper cage wound through it here. And we carefully weave the magnesium ribbon and kind of tie it on securely to the rubber stopper so that it doesn't fall off and create a really violent explosion or just lose your reagent.
Oh, dang, no violent explosions.
Setting the stopper on, the water's overflowing.
That's okay though, because the acid is at the bottom.
Acid's at the bottom. Inverting the discharge tube. Whoa, the dense acid is really shimmering, viscous, and slow.
We're gonna take this like off rails here to get a shot of the acid falling here. It's actually kind of cool.
Yeah.
Oop, that's just your arm.
Shimmering down. gradually making its way to the magnesium, which is now at the bottom of the tube.
I love that part. It's so cool.
Just at the surface of the magnesium ribbon. There we go. We have liftoff.
It's starting. Bubbly, bubbly. Now, if all goes to plan, see, Doug, the gas will be collected in the tube and not blow off the stopper at the bottom.
Correct.
Because that happens occasionally, or there's a huge leak. That happens also occasionally. Also, if our math is bad, we'll have collected way more gas than that tube can hold, so we'll have to start over again.
Wow, look at the vigorous production of hydrogen gas bubbles now.
So the cool thing is as the gas rises and displaces the water, there are gradation lines along the side of this gas collecting tube. We'll be able to measure exactly how much volume of gas is produced. This is the lab value, which you'll need later in the calculation. Okay, I'm gonna go back on rails here.
Yeah.
Whoop. In Vegas,
We're producing a lot of gas here. We've got magnesium left. Mr. Zed, it's unreacted. We're winding down.
we'll see. I was worried about the chunky size of that magnesium we were using, so. Oh, uh-oh.
Whoa!
Did it just stop?
We are good.
All right, sweet. Okay, do I have to? Okay, we're back. What are you doing now, Z-Dog?
Well, it's really important when collecting any gases to ensure that the pressure inside the gas collection tube is the same as the air pressure in the lab. So I'm adding water to this bucket so that the level of the water inside and outside of the gas collection tube are the same, thus ensuring the same pressure inside and outside of this gas collection tube.
Okay, what's the volume that we collected here, Z-Dog?
All right, when the water levels are at the same height, we collect 71.90 milliliters of hydrogen gas. And that was when 0.06 grams of magnesium were reacted with excess hydrochloric acid.
Okay, we'll get that all on the board for you guys at the end here. Okay, so you will need the data I'm going to write on the board for the questions that you guys are going to be working on this week. So there is gas Stoich questions and solution Stoich questions, and you'll need the data as part of the assignment. So our experiment, the lab value that was collected was 71.90 milliliters. Now, what you're going to have to calculate here is theoretical. So don't be putting this in your calculation to find the theoretical of this. This is your lab value, okay? You'll need this to do the percent error calculation in the question set. So this data you'll need. The temperature today, based on our really nice system here, I don't know if you can zoom in on that, Z-Dog, or just hold that up. Is that cool? So we've got this really cool temperature probe. Wave it around in the air like you just don't care. 2.1 degrees Celsius. Okay, make sure you convert that to Kelvin in your calculations. The pressure today on our barometer, which is kind of maybe broken, we checked with weather, like Government of Canada weather, is 100.8 kilopascals. And the mass magnesium that we used was 0.06 grams. okay? So this you're going to be using with gas stoichiometry and the R constant. Don't forget to use the R constant. We use the R constant. Remember when we talked, when a question has pressure and temperature, the R constant goes with that, to figure out the theoretical volume of gas produced. And then you're going to compare that to the actual or lab value that is produced. So you'll see in the question set, you have to balance the reaction, do the math, and find the percent error. And we've done the lab for you, and you guys are going to crunch the numbers. And that is gas stoich. Woohoo!